Okay, so today we're going to be looking at half-life and decay series, which is part of our area of study 3, what is matter and how is it formed? This is actually 6.4, not 6.3, but our 4 learning intentions are to describe nuclear transformations using decay equations, to describe the radioactive decay of unstable nuclei with reference to half-life, to apply and interpret decay series diagrams with reference to type and decay and stability of isotopes, and to model radioactive decay as a random process with a particular half-life relating to each isotope, including mathematical modeling with reference to whole half-lives. Okay, so let's jump in. This is actually the symbol of the Half-Life game, and this is, you might have seen the symbol before, but this is just a bit of a visual stimulant to introduce this idea of decay and half-life. Why is this measure required? Well, half-life is a random, or decay is a random process. So if it's random, then we need a way of measuring after a certain period of time, then statistically, when has half of this sample decayed, or if it's undergoing alpha or beta or gamma decay, then when will half of that radioactive sample be gone? And an analogy is to tossing a coin or rolling a dice. When we can assign a probability for a particular outcome, for example, heads or tails, but it's impossible to say for sure when the next heads or tails will be. We know that it's 50-50, but we can't say if it's going to be the next one or the one after. Okay, so half-life, its symbol that we use is T half, like to the subscript half. And half-life is defined as the amount of time for half of the radioactive atoms to decay. Just have a look at this simulation here. So the number at the top is how many half-lives have elapsed. It's the identical atom on the left hand and on the right hand side, but on the left hand side you start with 4 atoms per box, and on the right hand side you start with 400. So this is an example of, statistically, they should both become all white, both the left and the right hand side, at the same time, eventually, after an infinite amount of time. But as you can see, the sample on the right, the overall decay is more regular and more predictable. So more atoms means it has a better predictability. Okay. Let's have a look at this example here. This is taken from the book, and each one of these circles represents 1 million polonium-218 atoms. Now, if polonium has a half-life of 3 minutes, then after 3 minutes, half of these radioactive isotopes would have decayed. So after 3 minutes, statistically, there's 50 million left. Then after another 3 minutes, how many should be left? Half of the remaining 50. All right, this brings us to the idea of count. Count represents the number of nuclei that are left in the source that have not yet decayed. All right, well, let's have a look at a visual representation of a decay curve. So up here, after no time, okay, after no time, there are 6,000 nuclei. Then after a certain amount of time, they decay, and there is 3,000 remaining. So there are exactly half of the initial atoms left, which haven't decayed. This time it takes to get from 6,000 to 3,000, this is referred to as the half-life. So in this case, the half-life is 7. You'll note also the shape here. This is the shape of a exponential decay. All right, let's have a look at this decay curve here. You've got the number of thorium nuclei on the left-hand side and the time in days down the bottom. And it's given to you that the half-life, T half, is 24 days. So it takes 24 days to go from the initial 1,000 nuclei down to half of the initial, or 500. Have a go at answering this question. How many thorium-234 atoms will remain after 72 days? So first of all, try and figure out how many half-lives this is. 24 days is one half-life. So 48 is two half-lives. 72 is three half-lives. So let's step that down. 1,000 to 500 is one half-life. Then down to half of that again is two half-lives. And then half of that again would be three half-lives. Half of 500 is 250, and then half of 250 is 125. So after three half-lives, or 72 days, there will be 125 nuclei remaining. Okay, activity. Not let's do an activity, but the concept of activity. Activity is the source. How active the source is, or how many decays would take place in a given interval of time. Activity is measured in becquerels, BQ, capital B, lowercase q. All right, so very similar to our decay curve just before with nuclei, we can graph something interesting, which is the activity curve, or the amount of disintegrations per second, or counts per second, as you can see on the left-hand side over there. So if initially a sample was emitting 2 times 10 to the 4 disintegrations per second, and over 24 days, half of them decay, then there's not as many atoms left which are still emitting radiation. So logic dictates that the activity, or the rate in which the disintegrations are happening, also decreases. And this decreases at exactly the same rate as the nuclei decreases. Have a go at this example here. What will the activity rate of thorium-234 be after 2 half-lives? So after 1 half-life, 1 times 10 to the 4. So after 2 half-lives, 0.5 times 10 to the 4, or 5 times 10 to the 3 counts per second. Or BQ, becquerels. Okay. This is just a short picture about comparing activity. So something with a very, very short half-life, say polonium here, after 30 minutes, the activity has decreased very, very fast. So 30 minutes prior, here, on the left-hand side, 30 minutes prior, this was really, really active, emitting lots and lots of radiation. Now, it has a really short half-life, which means that all of those nuclei decay very quickly to something which is not very radioactive. Now, uranium, on the other hand, has a very, very long half-life. So the activity over a very long time does not change very much. Okay, just a concept check here, which I'll ask you to complete in your workbook, and then we can have a look at the start of the next lesson. the half-life of a substance affects the count and activity rate of that sample differently. True or false? So I want you to reference this example in your response. And you can just pause to complete this example now. All right, so you've resumed, so let's complete the notes here with the mathematical modeling of the number of atoms. This is the model which represents an initial number of radioactive nuclei, N0. Now we can calculate the number of, or the count remaining, if we have the initial, and we half it a certain number of times, or depending on how many half-lives have elapsed. Now, we can go one step further and say, okay, this number of half-lives have elapsed. If we don't know what that is, but we know the time period in which it's been decayed and the half-life of the particular atom, then we can work out how many half-lives have occurred. Similarly, per activity, we can use the same modeling, but replace N, or the count, with the activity of the sample.